Okay, so now we're going to be looking at this very important topic, which is forces. Now, since this is a very vast topic, we'll be covering it in some parts, and this is going to be the first part. We're going to introduce ourselves to the concept of forces and what are the main prerequisites that we need to know before understanding forces. So let's dive in. Now, what exactly is a force? When you think about a force, the first thing that comes in your mind is a push or a pull, or I'm sure that you've studied that before IGCSE too, that a force is a push or a pull. Now, what effect does a force have on a body? A force can cause a body at rest to move, or if the body is already moving, it can change its speed or direction of motion. A force can also change a body's shape or size. Now, this is not exactly the definition of force, however, it does tell in simple terms what it can be and what effects can it have on different objects that it is applied to. So let's think about some examples of how force in our daily lives can, result in these effects. So the first one is that a force is a push or pull. Well, if you think about applying a force in terms of pushing something, then a very easy example is that of doors that we push them and pull them to open or close them. So that is an application of force where we are pushing or pulling something. It can also cause a body at rest to move. Well, if a body is at rest, let's just say you have a toy car and it is at rest, then but you flick it or you give it a push, then it starts to move. So that's how, one example of how a body at rest can be put to move using a force. Similarly, if a body is already moving, it can change that. Similarly, if the car is already moving, you can put a hand in front of it and it will, you know, uh, brake. So the point is that is how force and its effects work. However, if a body can change, sorry, a force can also change a body's shape and size. Well, this part is very important for today's lecture, and we'll be covering a lot of this um, part. So, a force can also change a body's shape or size. What do you think of when you think that a force is changing something's shape or size? Well, the most common example is that of springs or clay or slime as they're used these days. So if you apply some force on a spring and I try to compress it, it is going to change its shape or size. It's not necessarily going to change its shape. It is going to be a coil or it is going to stay a spring, but its size is going to be reduced until and unless I do not remove that force that I am applying on it. So there's that. Weight. Now, before we get into the Hooke's law or other further concepts regarding force, I want to revisit the concept of weight. Now, weight. We all constantly experience the force of gravity, right? We have already discussed that every object with some mass experiences weight and experiences gravity. In other words, the pull of Earth. It causes an unsupported body to fall from rest to ground. The weight of a body is the force of gravity on it. Gravity is a force that can act through space. There does not need to be a contact between the Earth and the object on which it acts, as there is when you push or pull something. Other action at a distance forces which like gravity decrease with distance are magnetic forces between magnets and electric forces between electric charges. Now, the main concept that I'm trying to convey here is that force isn't necessarily supposed to be applied through contact. Force can be applied at a distance too. So this is basically where it tells that other action at a distance forces, like the other forces that do have some impact on an object, uh, even at some distance, even when they're not touching each other, even when they're not in contact with each other, exist. And what happens is that most of these action at a distance forces occur or take place when there is some um, when there is some field where they're applied to, like a magnetic field. magnetic field is something that is caused by a source that is uh, exerting some force on other similar related objects. Like if I have a very huge magnet that is lying on a table, then that magnet has a magnetic field and it isn't supposed to be touching some other magnets or iron materials. So that's an action at a distance force that magnet is applying force, but it is also applying it at a distance. And obviously, as it says that the further you move away from that distance, the lesser the force impact or the force effect it's gonna experience. Similar is the case with gravity. The closer you get to equator or the center of the Earth, the more you are going to get more gravitational effects. But since Earth is so huge and it is spherical, so the effects are not as negligible, but still we tend to neglect them and consider it as like a uniform gravity. Um, so next is that we all constantly okay. Um, Yeah, I guess that's about it. That the forces, the push and pull, isn't supposed to be just in contact. It can be at a distance too. And similarly, we've talked about magnetic forces. Similar is the case with electric forces. We're going to study that in detail in very last chapters. So, what exactly is the Newton? We have already uh, come across with this term of Newton, and it is basically based on the change of, and it's basically the SI unit of force. And previously we studied that it is the SI unit of weight. Well, that's also because weight is a force. Um, now, if you think about the basic units of Newton, the base units where how it is formed, then it is that F is equal to ma, force is equal to mass times acceleration. So force is equal to mass times acceleration. So Newton, which is the um, unit of force, is equal to kilograms meters per second squared. So that's how we know what Newton basically is. It is the SI unit, but if you represent it in terms of base units, then it is kilograms per meter, kilograms meter per second squared, because F is equal to ma, mass units into acceleration units. And another, there is this revision that the weight of a body of mass 1 kg is 9.8 Newton. Well, that's another revision that we've already studied. That's because the gravitational acceleration is 9.8 meters per second square. But then again, I've been using 9.81 or 9.8 in these slides, but it's okay and it is better to use 10 meters per second square acceleration in the main exam or the questions. Now we are going to talk about this very important law, which is the Hooke's law. And well, Hooke's law touches the part of force where we were talking about how force can impact in changing the size or shape of an object. So using the sign of proportionality, this is the sign of proportionality, we can write that Hooke's law as extension is directly proportional to the stretching force. Now, it does say stretching force over here, but it is going to be the same law if we change extension to compression and we change the compressing force to stretching force. So basically the point is that the force that we apply on a spring or on an object um, is directly proportional to the change in its length. So the more that you apply the force to it, the more the change in length is going to happen. Well, obviously, if you think about something having an impact on something in like such a uniform manner, there has to be some limitation to it because obviously you know this is not the ideal scenario, and in our daily life or real scenarios, there has to be a limit. So that comes in play when we talk about limit of proportionality or the elastic limit of an object. We're talking about springs because they are the elastic object and they are the kind of objects that demonstrate these behavior very easily. So it is. true only if the elastic limit or limit of proportionality of a spring is not exceeded. In other words, the spring returns to its original length when the force is removed. So the point is, what is this elastic limit? Elastic limit is basically the point of force after which when you unload your that amount of force, the spring does not retain its original length. Because before elastic limit, the spring was behaving in that pattern. So the thing what happens is that when you load something, so it stretches. However, when you unload it, it goes back to its original length. However, after a certain amount of load, it does not go back to its original length and it does stay very much stretched. So that's basically the problem that we are dealing here. Okay. That's not really a problem, I'm sorry, but I mean it's a limitation, and that limit is called limit of proportionality. It's basically called limit of proportionality because you're going to see that now in some time. It's very easily seen and it can be very easily studied on the graph. So I guess the graph is on the next page. Yes, here it is. We are going to study this very, very, very qualitatively. Okay, so the graph is for a spring stretched beyond its elastic limit. Well, before explaining what elastic limit is, how it is the elastic limit, I'm just going to tell you that this is the elastic limit. This one I'm highlighting right now. OE is a straight line passing through the origin. Okay, now this line from O to E is a straight line that is passing through origin. Yeah, and is a graphic proof that Hooke's law holds over the range. Okay, we are going to talk about that. If the force for point A on the graph is applied to the spring, the proportionality limit has passed. And removing the force, sum of the extension OS, this extension remains. Okay, now let's get into this. If you look at the graph from O to E, you can clearly see that there is a straight line, right? And when there's a straight line in graph with a positive gradient, that means that something on y-axis and something on x-axis is directly proportional to each other. So we do know that stretching force and total extension is directly proportional to each other. And how do we know that? We know that through what is written here, Hooke's law. Now this line stays straight till only point E, and it does start to bend and get into this plateau-like shape after point E. So basically the Hooke's law does hold true till point E. So this is basically the point where Hooke's law is held true. Now the thing is that what happens after E and what is this point E? Well, we've already discussed E is that infamous point known as the limit of proportionality or the क्या नाम है, or the elastic limit. You can see that let's just say at point E, if I have applied some force that is 15 newtons, right? And if I unload this 15 newton, the spring is going to get back like this. Like the extension is going to slowly decrease unless and until it gets back to point zero. There is going to be no permanent deformation or no permanent extension that it is going to experience. However, after point E, at point A, or let's say even after that, at this random point that I'm just labeling at point B, if the object is unloaded, it is going to go something like this. The extension is going to decrease, but there is going to be this permanent deformation. If I load it till B and if I load it till A, then there is going to be this permanent deformation known as OS. So beyond point E, we know that it has, since we have passed the limit of proportionality, so we have permanently deformed or just, stretched our spring. So there's that. Now, this is basically the whole explanation of Hooke's law, and I hope that understood it. Now we are going to go about some of the analysis and some of the points that we have learned so far about the Hooke's law. Now, we do know that F, which is the stretching force, let's just say, is directly proportional to X, which is the extension. But how do we change this proportionality sign over here to some kind of equality? We do want to have an equation formed. Well, for that, what we do is we equate it to F equals to some constant divided by X. Now, what is this constant exactly? Constant K is basically the force constant or the spring constant or the stiffness, anything you want to call it, of a spring, and it is the force needed to cause unit extension. Well, if I rearrange it to this form, here you go, K is equal to F by X, then it does give the look of force per unit extension. Then, like, how much force do we need for something to extend by 1 millimeter, if the unit of extension that we are talking about is in millimeter, or if we're talking about 1 meter, then how much force do we need to get something stretched to 1 meter? So that's basically it. And another thing to note, a very important thing to note, is that force constant K does not depend does not depend on the on the shape of the object, or on the configuration or the orientation or any other random um, feature of the object, or what shape it is cut into, or what is the size of it initially. No, the force constant only and only depends on the material of the object. It is a property of an object. The force constant of iron would be one value, of steel would be one value, whatever the shape is, whatever the size is, because force constant is basically the force needed to cause 1 unit of extension, right? So it doesn't matter what shape it is, what size it is, what orientation it is laid in, what kind of force you're exerting on it. So there's that one thing to note, that force constant is basically a material property. Moving on. Now, this is again a very important topic, and we're going to be studying this in some detail, but we are going to leave some of that detail for later chapters too. We are just going to touch the simplified versions of it. Now, why exactly do we need to add forces? If you think about any object that you experience or that you see in your real life, like even yourself or even anything that is lying on your table or is in front of you, if you look at it, you're like, hey, so weight is being applied to this object, right? Then why is it not moving? Or why is it not going inside Earth? Well, the point is that there is another force that is applied to it, that is called the reaction force, that it is applied by the the surface that it is put on, so that is lying on. So that's and that is basically why it is stationary. That reaction force and the weight are canceling each other out, and hence that object that you're looking at is basically stationary. Well, other than that, if we think about any other object, if we think about a car moving outside, or if you even think about yourself walking, there isn't just two forces, there are millions and so many of forces. What about the friction of my feet and the ground? What about the drag force, let's just say, in the drag force that I'm experiencing, the air resistance that I'm experiencing when I'm walking? Other forces, let's just say someone walks by me, the wind blows, there is that force. So the point is that there are so many forces that are being applied to it, and there isn't just one force that is always being applied to something if you look at it in a real life image. So when you're going to do questions, they are also going to be involving several forces. So forces and resultant forces have both magnitude and size, and direction, because obviously force is a vector. It is represented in diagrams by a straight line with an arrow to show its direction of action. Usually, more than one force acts on an object. Well, we have studied that. As a simple example, an object resting on a table is pulled downwards by its weight W and pushed upwards by its force R due to the. Well, we've already talked about that if we're talking about this object, which is apparently stationary, then we know that the weight is being cancelled about. It's being cancelled out by a force, and that force happens to be this reaction force that this table or whatever this slab is applying on this bowl of whatever balls or whatever that is. So why do we need to basically add forces when, like, it's fine if we have even a lot of forces. The reason is that when we are analyzing an object or where we're calculating something, the speed, the acceleration, or anything, it's better to have one magnitude of a force that we can say that if you combine the effects of all these random forces, what is going to be the magnitude or the direction and the direction of these combined forces. What is going to be the effect? In which direction is it going to move if it has to move, or in which direction will it change its size if it has to change its size? So the point is that it is very much important to find the resultant force instead of having one simple force. Now we're going to study how we're going to basically do that. It's pretty simple. So the basic rule is that right now the kind of questions that we'll be looking into, we will be looking into other questions in detail after uh, some lectures. Once we're done with the forces, we're going to analyze that. But for right now, what you need to understand is that if two forces are in the same direction and they are in the same line, this both of them are pointing towards, in this case, they're pointing towards right. So they are pointing towards right. I do know that the resultant or the final force, the combination of these forces is going to point towards right. So I'm just going to draw. Now what's going to be the magnitude of these two forces combined? Well, 1 plus 2, like in this case, 1 plus 2, we add them because they are in the same direction. They are not opposing each other. They are they are reinforcing each other. So 1 plus 2 is equal to 3. So that means that the resultant force is 3 in the right direction, in the direction where both of these were applied. Now what happens if the direction is different? Well, before talking about the magnitude, it is important to talk about what direction will our resultant be in. Well, the resultant will be in, sorry, this is 2 and this is 3. So the resultant is going to be in the direction where the larger force was being applied into. So I do know that the resultant is going to be in the right direction again because 3 is the larger of these two and it is being applied in the right direction. Now, what happens is that you add these two forces again. But how exactly you do that? Okay, what you do is that you take conventions. In this case, this is the axis that we are talking about. So this is the y-axis and this is the x-axis. Now we do know from our basic knowledge that upward pointing means positive y and rightwards pointing means positive x, right? And in this case, all of the arrows are in the x direction, so we are not going to be thinking about the y factor. We're just going to think about the x uh, direction. Now, in which direction is 3 Newton arrow? Well, 3 Newton arrow is in positive x direction. So I'm just going to write positive 3 Newton. Now, in which direction is the 2 Newton? Well, 2 Newton is in this direction towards left, which is the negative y direction, negative x direction, negative. So I'm just going to write minus 2 Newton. Well, 3 plus 3 Newton minus 2 Newton is equal to 1 Newton, and that is going to be the magnitude of our basically resultant. Well, in these cases, the thing to note is that both of these arrows are in the same direction. They're not pointing, like, it's not necessary that they are pointing in the same direction, as in they both are pointing towards right or left, but we can see that they both are in the x direction. This is a simple case, and for now, we are just going to study this. However, later we will be talking about, or we will be looking into forces that will be in random directions. Let's just say like this, and like this. So we will have to look into these random forces and then account to their resultant. But for now, this is enough. and we will be moving forward. Let me erase all these ink on the slide. It is often useful for the design engineer to know the value of single force, i.e. the resultant, which has the exactly same effect as these forces. Well, we've studied that and we do know the reason why we need that. So if the forces act in the same straight line, the resultant is found by simple addition or subtraction as shown. So that's basically it, that if the direction is same, you are going to add them, and if they're not the same, you're going to subtract them, or even if you use that um, the the convention that I just showed you about the x and y, and you just look at those signs, then also you are going to get to the right direction. So this law is only applicable for cases in which the forces act in the same direction. However, by same direction means that if they're parallel. Another thing that I want you to know, that if there's an object like this and there is a force that is applied to it like this, and then there's a force that applies to it like this, you can also add them. They don't have to be in the straight same line. They just have to be parallel to each other. Whether it be like this or it be like this, all three of these arrows, this one, and this one, all of them can be added because they are parallel to each other. Okay, now we are going to be talking about this very important part, this last part, which is basically friction or resistive forces. Moving forward, now what exactly is friction? Now friction is any kind of force that is resisting or um, that is opposing the motion. Friction is a force that opposes one surface moving or trying to move over another. If there are any two surfaces that are lying on each other and then they're moving or have a relative motion to them, it is for sure that friction exists between them. Well, friction can be of help and of hindrance. First of all, it is very easy to just think of friction as hindrance because um, that's how we've been thinking about it. Let's just say in our machinery, when there is power production, we're like, um, machines are, obviously relatively moving to each other, and there is a lot of friction. And to remove that, we apply lubricants and everything so that they're more smoother in action and everything. But what the thing that we most of the time forget about friction, that it is helping us in so many ways in our real life, um, is that of a biggest example. And if you think about it, is that when we're walking, we can only walk because there is friction. Because the reason why we cannot walk on oil that easily or on water when it is spilled on the ground is because the friction factor reduces. There is less friction. So the friction that is between our sole or the even our foot or even the ground is what does not make us slip backwards, and it lets us take rigid steps and not make us slip backwards because there is friction. And but if you think about, if there's a lot of oil spilled on the ground and you try to walk in it, well, there are huge chances that you slip. Well, that's because there would be very less friction or no friction. Okay, on the other hand, engineers try to reduce friction. That is the point that we've talked about. That is the point of friction as a hindrance or a problem, which is very detailed topic, and it is very much affecting every area of life that we've also talked about. Moving forward, when a gradually increasing force P is applied through a spring balance to a block on table, the block does not move at first. This is because an equally increasing but opposing friction F force acts with the block and the table touch. Now, this says that if the driving force, that in this case is P, is equal to the friction force, which is the opposing force, then obviously an object will not move because they both cancel out each other and the resultant force is zero. If P is increased further, the block eventually moves, and it does so. F has its maximum value called starting or static friction. Um, you don't have to basically get what these terms static or starting friction are, but basically what I'm trying to convey here is that friction or resistive forces tend to catch up with the normal forces or the driving forces that are applied to. Biggest example is that of something falling through air, if we do not neglect the air resistance factors, then we know how terminal velocity is reached. And that basically happens, yet it is written over here that initially when an object is falling through air, the the main force that it is experiencing acceleration because of its weight, and initially the acceleration is 9.8 meters per second because it's just weight and weight only. But by the passage of time, the air resistance increases and it catches up. It catches up and decreases acceleration unless and until it becomes zero, and when the weight and the air resistance is both equal to each other. So that happens. Um, and that basically brings the falling object or the parachutist or whatever we're talking about to terminal velocity, a constant velocity, zero acceleration, because the what do you call it? The 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 resultant force was equal to zero in the end. The force of air resistance is often observed to oppose the motion of our object. This force will frequently be neglected due to its negligible magnitude and due to, yeah, it will be mostly neglected when we're talking about free fall, like a ball or something. However, if you're talking about huger, bigger objects, heavier objects, or larger surface areas like parachutists and everything, then they will be, need to be considered. That's about it. And